So, solving right triangles I mentioned a little bit, and it's where we solve for all of the angle measurements and all of the side lengths. So basically we want to complete the triangle. So any missing information, we want to fill in the blanks. Now with some of these, specifically ones that deal with 30, 60, and 45, we can kind of skip using our trig functions. So I'll show examples with that. But then as we'll see with cases down here, like with 65 degrees and 81 degrees, those aren't special triangles. I'm sure they're special in their own way, but not special to us. So with that, we're gonna need our trigonometric functions there. So I'll show you both ways of solving it. With these, when we have a 30, 60, 90, we could use those trig functions. It would give us the same answer in the end, but I kind of want to show us some different ways of solving it, getting used to the properties of these triangles. So what I can notice with this one is that we're missing two side lengths. Sorry, that's quite blurry there, but we're missing A, we're missing C, and we're missing an angle here, but I can fill that in real quick because we have 30 and 90, which means that needs to be 60 degrees. So here's one of the pieces. And then I just need to figure out what is C equal to and what is A equal to. So I just need to find those values. Now I can't just use the Pythagorean theorem here because we're missing two side lengths. So I have two unknowns, so I don't want to plug into the Pythagorean theorem yet. But we could use is the trick that we used when we looked at the special triangles, which is, let's think about what happens if I reflect that. So I would have a right angle, this would be 7, this would be C over here as well. But really what we would have are these three side lengths should be the same since it's equilateral. So where we have an unknown C, what we do know is the side length down here, which is 14. So that 7 and 7 together is making 14, which means C has to be equal to 14. So with that, now I have two of my side lengths. I have a 7, I have 14, and I will need to solve for what A is going to be equal to. So now we can plug into the Pythagorean theorem. So C is the hypotenuse, so we're going to have 14 squared alone on one side, and the other side will have A squared plus 7 squared, so equals 14 squared. And then I'm just going to solve through. A squared is equal to 14 squared minus 7 squared. Then I'm going to end up taking the square root, and I could just plug all of that into the calculator at once. So A is equal to, and I'll go ahead and show you this on the Desmos calculator, square root 14 squared minus 7 squared. So a 12.12. And with that, we solved the triangle. So we have all of the side lengths, all of the angles filled out, and we just need to use a little trick in order to find those side lengths. Something I do want to show you with this is that we could have actually skipped the Pythagorean theorem here. The fact that this is a special triangle, so remember when we looked at it and it had a hypotenuse of 1, that short side was 1/2 and this long side was root 3 over 2. Well, what we can see is this kind of scaling, like where we have the hypotenuse of 1, that scaled up to 14. This 1/2, so let me even write this down here. So 1 went to 14. That 1/2, well, what if we take 14 times that 1/2? Well, that gives us our 7. So then what happens if we take root 3 over 2 times 14? Well, if you plug that into a calculator, surprise, surprise, it's 12.12. So for these cases where you have a special triangle, if you get out your hypotenuse, and it has to be the hypotenuse because that's your special kind of scaling of 1 to another number, then what you can do is using multiplication, scale the other sides, and you could skip the Pythagorean theorem. So let me show you how to do that with this one here. I think I can, Oh, I think the hypotenuse comes in last here, so we're going to be stuck with the Pythagorean theorem here. All right. Something we could use, though, is this relationship that this value at the bottom here, so the short side length, is half of the hypotenuse. So what we could use here is that, so we have the short side length of A, so that means C should be 2 times that side length. So we can use that relationship. Or we could have done it as C over 2 on that side. Basically, we want it in terms of a single variable. So either way, I'm just going to avoid fractions as much as I can. So I'm going to use that 2a there. So this means that I have 2 unknown side lengths. However, I can represent it in terms of a single variable. And then let's see, C is our hypotenuse. And then we have leg of A, leg of 10. So that means that 10 squared plus A squared is equal to our hypotenuse squared. So we're going to have that as 2A instead of C because we don't want to introduce another unknown variable, and that'll be squared. So 100 plus A squared equals 4A squared. Subtract A squared from both sides, and that'll leave us with 3A squared. Divide by 3. Take the square root. So A is going to be the square root of 100 divided by 3, which, ooh, sorry about that, is about 5.77. So let me go ahead and grab an exact value because we're going to need that to calculate the hypotenuse as well. So square root of 100 over 3. So 5.77, and then for the hypotenuse, I just want 2 times that number, so 11.55. So this is going to be 11.55, and this is going to be 5.77. And the only other missing piece is angle measurement, 30 degrees. So that's how we can solve triangles if it's one of our special triangles. But now let's look at the non-special triangles. So we can fill in the blank for that third angle by using that property of 180 degrees. So all 3 angles should add up to 180. So we're going to always be able to take out a 90. And then in this case, we're also taking out a 65. So that should leave a measurement of 25 degrees. So B is 25 degrees. Now, I need to solve for these unknown side lengths. However, we can't use the Pythagorean theorem because we have 2 unknowns. And then because this is a non-special triangle, I don't have a way of relating them to each other. And this is where our trigonometric functions come in. So what I'm going to do is choose one of the angles, 25 or 65. What I typically do is I go for the one that's printed on my paper, just in case I made an error with that calculation. If I just typed it in wrong for some reason, using the one that's printed on the paper is just kind of safer so that you're not repeating an error. So that if we made a mistake here, if we use this printed angle, then maybe all of our work for the other pieces is correct, and the only thing we'd miss is this. However, if I made an error here and then I used it in all of the trig functions, that's not good. Then everything will be wrong. So I typically go for the other. However, if this angle is correct, then it should all work the same. All that's going to change is what you're calling opposite and adjacent. So with this, we have our hypotenuse. We're calling A would be opposite, and B is going to be adjacent. So let's say I want to solve for A. What I know, like the information that I have, is I know I have a measurement of 65 degrees, so I know my angle. I know the hypotenuse. And what I want to find is the opposite. So what I need to do is make sure that I choose a trig function that's relating, well, all of them will relate the angle, but I want to find one that uses opposite and hypotenuse together. Now there's two options. There's sine and cosecant. So we have those reciprocal functions. Again, I'm just going to write these off to the side. So katoa, we generally just focus on these three when we're solving. So to relate opposite and hypotenuse, I want to use sine because I don't want to use adjacent, so that throws out cosine and tangent. So what I'm going to have is that sine of our measurement of 65 degrees is equal to opposite, which is our unknown value of a, over our hypotenuse, which we do know is 10. And what I want to do is solve for a. So what I would do is multiply both sides by 10, multiply by 10. So what I'm getting is that a is equal to 10 times sine of 65 degrees. Now, this sine of 65 degrees, I want to simplify down. And if it was a nice 45, 30, 60 value, we could do that using our special triangles. But like we talked about, this isn't a special triangle. So because I don't know what happens with a 65 degree triangle, I need to use a calculator. So what we're going to do is plug this in. So I'm going to go to the calculator and do 10 times sine and 65 degrees. And with that, I just double check that I'm in degree mode, which we are, and that's a 9.06. So that is one of our missing side lengths. That right there is equal to 9.06. Now, finding the third side length, we could go the trigonometry route. We could use cosine, or we could use tangent, because now we know opposite hypotenuse and we want to find adjacent. Or you can just use the Pythagorean theorem. Now that we found those two side lengths, we could just go to Pythagorean theorem. We have our side length 9.06 squared plus our unknown side of b squared equals 10 squared. So b squared is going to be equal to 10 squared minus 9.06 squared. One little issue with this is that 9.06 is rounded, but should be close. And then I just take the square root of both sides. So b is coming from the square root of 10 squared. So 10 squared minus 9.06 squared, which is 4.23. And I have a solution where I solved with the trigonometric functions and it came out to the same thing rounded. So we're not too far off. 4.23. So that right there is 4.23. Now, with solving triangles, it can be kind of difficult to check your answer. I mean, to check your answer, you could plug it all into the Pythagorean theorem and make sure that it truly is a right triangle. Something I do is I just kind of check that the hypotenuse is in fact the longest side, or if the figure is drawn to scale, seeing that, okay, this long side being 9 makes sense with this shorter side being 4, and our hypotenuse is the longest side of 10. That relationship should be there. So like when we go to this next example, I can see I have these two very long sides, and they're a lot longer where this is 16.5, so I have kind of a scale in mind. What I also can recognize is that C is the hypotenuse, so whatever I get for C, that should be the largest side length when I have all three of them filled in. All right, so 81 degrees, that means we're missing 19 degrees. So I'll fill in for A there, 19 degrees. In terms of using a trig function, I'm going to focus on being here at 81 degrees. So if we're at 81, let's see, we have hypotenuse. I'm going to use a different color. Sorry, I'm kind of using blue for the answers. So hypotenuse, which means B is opposite. 16.5 is adjacent. All right, opposite, adjacent, hypotenuse. So solving for, and we can choose whichever we want to. Let's go just alphabetically. Let's go with B. So solve for B. So we want to find opposite. We know the angle measurement. We know adjacent. So we have adjacent and we have the angle. So with this, what I'm looking for is a trig function that deals with opposite and adjacent. And that's going to be our tangent function. So if I take tangent of 81 degrees, I should have opposite divided by adjacent. So opposite is the unknown of B over adjacent, which is the 16.5. And I'm just going to multiply both sides by 16.5. So B will be equal to 16.5 times tangent of 81 degrees. And with that, I need to go to the calculator. So 16.5 times tangent of 81. And that's 104.18. So that's our side length for B is 104.18. And that makes sense. If this is 16.5, this is a lot longer than 16.5, so that makes sense visually. Now let's solve for C. So we can use our Pythagorean theorem, or you could use more trig functions. If you use trig, you would just want to relate hypotenuse to one of the side lengths. We've had a lot of practice with Pythagorean theorem. Let's go ahead and use a trig function. So we want to find the hypotenuse. And we know opposite and adjacent, so really we could choose. And we know our angle. Something I'm going to do is I'm going to use adjacent just for the same reason as why I chose 81 degrees and not 19 degrees. I like to go with the ones that are printed on the paper. Again, because I found this 104.18 just in case I made an error there, or especially like that's a rounded value, so to use it again will introduce more error. So I just like to go with the values that are printed on the paper. When I have a choice between one that I found and one that's printed, I go with the one that's printed. So I want to relate the hypotenuse and adjacent, and that's going to be cosine. So cosine of 81 degrees, we'll take our adjacent side length, which is 16.5, over unknown side length, which is C. So this one's going to take a little more maneuvering. I'm going to multiply both sides by C, which will get C to cancel out on that right-hand side. So I'll have C times the cosine of 81 degrees is equal to 16.5. Then what I need to do, okay, let's go ahead and write that out. C times cosine of 81 degrees equals 16.5. And something I should note is that this cosine of 81 degrees, it moves as a block. Cosine's the name of the function. 81 degrees is trapped inside the function. At no point is 81 just going to pop outside and become part of our calculation. That's all function notation there. So what I'm going to do is divide everything by this cosine of 81 degrees. So with that, I can solve for C with this 16.5 divided by cosine, which I need a calculator for that. Cosine of 81, and that's 105.48. All right, so if I go back to my triangle here, C is 105.48. Now, I just kind of look through, my hypotenuse is the longest side, so we're good there. I can kind of compare and contrast. Those are close to each other, but visually, that makes sense. Those are going to be pretty close, especially with such a small degree measurement between those. All right, so that is solving right triangles, either using just kind of rules of geometry and then using trigonometry to help out.